Next, let us take a look at the wave pressure equation. Now, in the water column or under the surface of the water, the pressure is made up of dynamic pressure, which is due to the wave motion, and also static pressure. The static pressure is made up of two components. One is due to the atmosphere, which is relatively small and negligible when compared to the hydrostatic pressure due to the water column above the point of interest. So in this case, we will only consider the hydrostatic pressure. So if imagine if we put a gauge, a pressure gauge in the somewhere in the water column, and we will be measuring the hydrostatic pressure plus the dynamic pressure. Hydrostatic pressure being a constant which depends only on water depth, and dynamic pressure due to the wave, which has a expression which we are getting familiar with. Now let's take a look at the hydrostatic pressure. Okay, you notice that the term is negative rho g z, and remember z is always a negative value, and it depends on the distance from the still water level. So rho g z is basically the hydrostatic pressure, which is positive. All right. And let's now look at the dynamic pressure. The dynamic pressure is rho g multiplied by k multiplied by eta. All right, rho g multiplied by k and then multiplied by eta. Eta is basically the water surface displacement, and k is the hyperbolic term, which again depends on the position in the water column. So it is very long expression, but you notice that we can actually simplify the whole expression to look like this only. Alright, so rho g times eta times k minus rho g times z. Now take note that since we are dealing with coastal environment, so the density of the water typically will be in the range of 1020 to 25 kilogram per meter cube. One thing to take note regarding the pressure equation is that it is only applicable below the still water level line. That means below z equals to 0. In this case, we can see that, for example, the blue triangle indicate the hydrostatic pressure distribution, which is 0 at the still water level in all cases. However, the dynamic pressure may increase or decrease depending on whether at any position it is the wave crest or the wave trough. If we go back to the equation, then you will notice that for a fixed position in the water column, the hydrostatic pressure is already fixed, but then the dynamic pressure component may be positive or may be negative, so that the total pressure may be less than hydrostatic, or the total pressure may be more than hydrostatic. If we rearrange the pressure equation, it can be written in this form, which is a useful form to estimate the wave height, meaning to say that we can install a wave gauge in the water column to measure the pressure fluctuation P, and if we know the location, the Z of the pressure gauge, then we are able to calculate the pressure in all these terms in order for us to derive what is the wave height that causes the pressure that we observe. Now in this arrangement, you notice that of course we still have the K, which is the pressure response factor, which depends on the water depth and also the position of our wave gauge. and also it depends on the wavelength. That means in order to be able to apply this equation, we also need to know the wavelength. N is a correction factor which depends on wave period, the wave height, and also the water depth. Typically, the correction factor will be more than 1 for long wave or less than 1 for short wave. And if we have a monochromatic wave, a linear wave, then there's no correction factor required. Usually this wave gauge or the sensing device is located at the water depth D, which is less than L/2. Remember, that is where the wave oscillatory motion is important, so that the recorded pressure fluctuation can be used for the purpose as mentioned. Let's look at one example here. An average maximum pressure of 124 kilonewton per square meter is measured by a subsurface pressure gauge located in salt water 0.6 meter above the bed in a water depth of 12 meter. The average frequency is 0.066 cycles per second. So that actually allows us to determine the wave period, which is the reciprocal or the inverse of the wave frequency. So here we have a 15 seconds wave based on the frequency. And since we know the wave period, we can calculate the deep water wavelength, which depends on only the wave period, equals to gt squared over 2 pi. And since we know the water depth is 12 meter, so we also able to find out what is the relative depth DOL, and in this case we have 0.07, which is close to shallow water condition. Since we already have DOL and L itself, so basically we are able to calculate the pressure response factor Kz. So this is the value that we obtain. And remember this equation, the left hand side is eta, which basically is the water surface displacement, and so it equals to the amplitude h over 2 during the maximum pressure condition. Under the maximum pressure condition, P is equals to 124, which is the value that we observe. Rho is the seawater density, G, and then Z is negative 11.4, because we have a 12 meter deep water and the pressure gauge is located 0.6 meter above the bed, so it is 11.6 meter below the still water surface. That's why it is negative. And then we have rho G and K from here. So using this, we are then able to calculate the wave height that produced this pressure, and the answer here is 2.08 meter. In this case, the correction factor N is equals to 1. Alright, since we are not given any specific information about the wave type or wave condition, so in the solution here we have not applied any specific correction factor, so we use 1, assuming that it is a linear wave.